Welcome to the Plague Doctor channel.
Here on the bench we have the Alamo Challenger. This is from somewhere around 1965. It's kind of similar to a Champ. It has three inputs here, all with the same impedance. One 12AX7, one 6v6, and a 5y3 rectifier. This has all ceramic capacitors inside. What we're going to do with this is rewire it somewhat like a Fender 5f2-A circuit with a few added things. This transformer here has 3 lugs coming out, so I'm going to test it and see if I have different impedances. Maybe one for a 4 and an 8 ohm speaker, or an 8 and a 16 ohm speaker. Here I have the output transformer hooked up to my Variac. We're going to figure out what the transformer impedance ratio is. Right now I've got 100 volts on the primary side, and on the secondary side, the yellow channel, I have 3 volts RMS coming out, and on the red channel I've got 4.25 volts RMS coming out. Next we're going to calculate the turns ratio. To find the turns ratio, we take the voltage on the primary and divide it by the voltage on the secondary. So the turns ratio for the yellow channel is 33.3 windings on the primary to 1 winding on the secondary, and the turns ratio for the red channel is 23.5 to 1. Next we're going to calculate the impedance ratio. To find the impedance ratio, we square the primary number, and that will be the impedance ratio to 1. So 33.3 squared to 1. So the impedance ratio of our output transformer for the yellow channel is 1100 to 1, and the red channel is 550 to 1. If we look in our tube manual under 6v6, which is what our output tube is, under the Class A configuration, at around 350 volts, we're going to want about 8500 ohms for the load resistance. So for the yellow channel, if we put an 8 ohm load, it'll reflect about 8800 on the primary side. If we put a 16 ohm load on the red channel, it'll reflect an 8800 ohm load on the primary. So what we have here will be ideal for an 8 and a 16 ohm speaker. I'm going to be replacing these input jacks, so we can go ahead and take these off. I'm also going to be replacing these potentiometers with something a little different, so we can go ahead and take these off also. Here I'm at a stopping point with this amplifier. I've installed 2 input jacks and a toggle switch. I've emptied out the underside, disconnected the can capacitor that came with it, and redressed all the wires. I've twisted the heaters and tucked them real close into the corner here so they'll be out of the way. This is a good stopping point for now until I get some stuff in the mail. Here I have the Alamo Challenger. I've got a lot of things wired up so far. The power cord comes in here. The hot wire goes through a fuse into the switch. From the switch it illuminates the pilot light and goes into the transformer. The neutral of the transformer returns to the power cord here, as well as the pilot lamp. The center taps of the secondaries are grounded here. This green wire is the filament line for the 6v6 and the 12AX7. The high voltage then comes off here, goes through a 470 ohm 5 watt resistor into the first filter capacitor network. I have two 47 microfarad at 400 volts in series with bleeder resistors going to ground. I then have a 1K resistor going from the first node to the second node here, where I have another set of capacitors in series to ground as the second filter capacitor. The reason I've done this is because the voltage off the secondary is somewhere around 460 to 480 volts, and the 6v6 doesn't need that much, so I'm using this network to drop the voltage down to a usable level for this amplifier. Also, I didn't have any 500 volt capacitors, so I put these two in series with bleeder resistors to make this about 23 microfarads at 800 volts, both of these. From here, the B plus comes over to this node, where there's another 1000 ohm resistor to the first power node that goes through the transformer into the 6v6. Then I have a 4.7K coming over to this filter capacitor that goes to ground and comes over to the screens. The screen is connected to this node, which is where the 12AX7 gets its B plus from. This is a 220K and this is a 100K. The inputs come in here. I have a low impedance and a high impedance input. The inputs come in here through a normal Fender input network. The next thing I'm gonna do is wire up these two potentiometers and switches. I have them set up on the outside of the chassis here to make it easier to wire up, and then I'll take these off and just put them in the holes over here and finish wiring everything up. Later on I'll explain with the schematic exactly what these switches and potentiometers do. This one is the volume potentiometer and this one is the tone potentiometer. I've also got push-pull pots here that do some fancy little things, and the switch here. So here I have everything all wired up for the most part. I have a couple resistors here that I'm not completely sure of their value yet. I'm pretty sure they're correct, but I'm gonna do some verifications. I'm just gonna go through with my ohm meter and verify everything is hooked up correctly. And then I'll go through and explain the schematic, how everything works, all the switches. First, I'm gonna make sure that there's no voltage. There shouldn't be because it hasn't been powered up. So the first time I powered this up, I got up to about 60 volts. And then you could hear a noticeable hum. When I touched the volume and tone pots, it would go away. And I didn't ground these specifically. Any ground that they would be getting was coming from the chassis. There's ground coming from this shielded connection going into the tone network, and all the circuitry here is grounded through that. So these weren't necessarily grounded, so I added these ground bars to see if that gets rid of that. So let's give it a try. So here the amp is. It's been sitting for a couple minutes, kind of stabilizing. I figured out the issue with the hum was that the leaves here on the input jacks actually were lifted up a little bit, so the inputs weren't actually grounded. As you can see, here I have both the volume and tone knobs turned all the way up, and as you can hear, it's absolutely dead quiet. This is what the output looks like. Here I have it set at 5 millivolts per division, and I'm getting a little bit of some wiggle on the output that's about 1 millivolt RMS. So this thing is very quiet. I'm going to hook a signal into the front of it. I have the cathode resistor for the first stage of the input just tacked in here. I'm going to verify that that's the correct value so that at the point where I push it to distortion, it clips fairly evenly. Here I am with the amp. I'm going to bias the 6v6. When I put this together, I biased it pretty cold at about 6 watts, and I'd like it to be about 11 watts or so. Currently the cathode resistor is 888 ohms. I think I'm going to put in a 470. So I've changed out this resistor, and the bias resistor with 470 ohm resistors. I now have about 304 volts at this node, and I'm passing about 30 milliamps of current, which comes out to about 9.1 watts of plate dissipation. Here I have the amp hooked up to a 100 hertz sine wave. I'm going into the low input with a 100 millivolt peak-to-peak signal. With the volume on 10, I have about 2.1 watts clean power. When I flip the clip switch, you can see the waveform changes, and I have about 3.3 watts of power output. With the clip switch on, I'm at about 6.5, 7 with a clean sine wave out, and then as you go up, it starts clipping. Now if I pull the volume switch out, it disengages the negative feedback, puts a bypass capacitor, 22 microfarad, in the second gain stage of the 12AX7. And right about there is about 2 on the volume before it starts distorting. And that's with the volume at 10. Now if I engage the clip switch, here the volume is about 1.25 maybe with a clean sine wave before it goes into distortion. This switch here engages a low cut switch. I'm gonna have to change the capacitor and the tone stack to make it more effective. At 100 hertz, it does about 0.6 volts of cut, and that's really low. So I'm gonna alter that and see if we can't get more bass cut. Here's the capacitance substitution box I made in another video. The capacitor I just took out was a 1 nanofarad. I'm gonna turn my signal generator up to 500 hertz. I'm going to plug in a capacitor here. I'm gonna try tacking in a 470 picofarad. At 100 hertz, it now goes from about 4 volts, 3.97 RMS, down to 1.62. At 500 hertz, it goes from 4.05 volts to 3.65 RMS. Here's 900 hertz at 4 volts, and now 3.89. So I think that's the value I'm gonna use. The next trick is to get this capacitor back inside there where I took the old one out. That's gonna be a trick. Here the amp is all finished up, and I'm going to go through and explain the schematic and the way I've constructed the amp. Construction is all point-to-point wiring. The inputs here have been soldered to the chassis. These ground lugs here have all been soldered to the chassis. Every one of these terminal strips, the ground lug, has also been soldered to the chassis, here, 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 and even here, and here. The two potentiometers and switches on the front here have a ground bar that goes from here to here and is tied in here. And all this gives individual star grounding points for every ground location, so that there's no ground loops. Walking through the schematic, here's the power supply section, and that's here. This is the line cord coming in. The hot wire goes to this lug, goes through a 1/2 amp fuse to the power switch, and then from the power switch it goes into the transformer, and it also lights this indicator light, which comes back to the neutral and out. These two yellow wires are the 5-volt winding for the 5Y3. The green wires are the filament windings for the 6v6 and the 12AX7, and the red wires are the high voltage coming into the rectifier tube. From the rectifier we go into this 470 ohm resistor, into the first filter capacitor, which is 2 capacitors in series with 2 470k resistors in series to make sure that there's equal voltage across them. These are 450 volt capacitors, and to make sure I didn't go over the rating of the capacitors, I doubled them up, so these are effectively 900 volt capacitors at about 23.5 microfarads. So then from this node we've got another 470 ohm resistor to here we've got the same setup, 2 capacitors with 2 resistors in parallel. From there, the high voltage comes over to this node, and there's another 470 ohm dropping resistor that goes to a 33 microfarad capacitor. This node goes into the transformer and then to the plate side of this 6v6. So we've gone through this 470, this 470, and this 470 into the plate of the 6v6. This is a 4.7k resistor. It goes to this node, which goes to the screen of the 6v6, which is here. There's also a filter capacitor here going to ground, and from the screen we have this node and this node, which feed high voltage into the 12AX7 plates here and here. So that's the power supply. On the front end, we've got 2 inputs wired in a Fender configuration, so there's a high input and a low input. I used shielded cable here that's grounded on this side. The low input comes to this node and goes into the grid, and the high input comes to this node and goes to the grid. This side of the 12AX7 has a 220k plate resistor and a 2.7k bias resistor with a 22 microfarad bypass capacitor, which is here. From there, the signal goes through this 22 nanofarad capacitor, which is here tucked under the bias network, which goes to this node here. From there, the signal goes through this shielded cable into the tone circuit. This tone circuit here is loosely based on the Moonlight tone circuit, which you can find on the internet. This switch here is a bass cut switch, which is here on the tone knob. So when it's pushed in, it's in this configuration, which bypasses this 470 picofarad capacitor, which allows the bass to go through into the signal onto the next stage. When it's pulled out, it breaks this circuit here and puts this 470 picofarad capacitor in circuit, which reduces the bass up to around maybe 500 hertz or so. This potentiometer here is the tone knob here, which is connected to this push-pull pot switch here. So these two are connected. This is the volume potentiometer, which is here. For both of these capacitors, I used mica capacitors, and all the resistors in this circuit are 1 watt metal film. These larger ones are 3 watt metal film, and this is a 5 watt. The signal comes back in here through this shielded cable to the second stage of the 12AX7. On the bottom of the 12AX7, we have a couple switches. This switch here is the large toggle switch we have on the front of the face here. When you flip it up, this 3.9K is biasing the 12AX7, which biases it very cold and allows the bottom part of the signal coming through the 12AX7 to get clipped off. And when it's down, this 2.2K is in parallel with this 3.9K and biases it in the middle of the operating range, so when it drives into distortion, it clips evenly. Over here, this switch is the switch connected to the switch on the volume knob, this push-pull pot. When it's in the out position, it allows this 22 microfarad bypass cap to be put into the circuit, which allows a significant amount of gain increase in this 12AX7, allowing it to distort sooner. When it's in the in position, it allows negative feedback from the output stage to come in through this 6.8K in here, and I chose this 6.8K through trial and error, so that on 10 there was minimum distortion. From this 12AX7 plate, we go through this capacitor, and we have the 470K resistor to ground and a grid stopping resistor, 1.5K, into the grid of the 6v6. Here's the bias network for the 6v6. So this is a 22 microfarad and a 4.7K, and that's how I've chosen to construct this very unique circuit. It's loosely based on the Fender 5f2-A Princeton, but most of the front end here is different with the addition of negative feedback. It has a 3-prong power cord with a dedicated ground, and the fuse is a 1/2 amp fuse. At full volume, it pulls about 0.34 amps. All the filament lines are twisted and tucked as far over into this corner as I could get them, and all the circuitry is up on this side or up in the air as much as I could get it away from the filament lines, and the circuit is extremely quiet, even with it exposed here on this side. Here I have the amp plugged into my 212 cabinet through the attenuator that I made. This is so the wife doesn't yell at me when I crank it all the way up. Here, if I turn the volume all the way up, you can hear it's absolutely dead quiet. Here with the volume and gain all the way up, you can hear a little bit of hiss from the high gain, but there's almost no noise. It's got a very low noise floor. There's absolutely no hum. Here I'm going into the low gain input. Clip switch is off, volume on 1, tone is on 5. Both switches are pushed in.